the University of Illinois, and he's working on a Martingale framework for trust.
Get this back up. Good afternoon. I'd like to speak today about a Martingale framework for trust. This is an elementary talk with no theorems. Maybe it's more of a research proposal, and I proposed that some of you think about the problem and see what you think. It's something you could use in an elementary class, and it's a good talk for me to give the day after I flew here. I don't have to worry about jet lag being a big problem here. What's this? Cancel. All right. Let's see. I have to get this going. You do it, but do it. Yeah. What? I think I have some interference with that. Cancel. All right. Okay, so I'm going to talk about network models and probing strategies, and then some performance analysis for one link, and then analysis for many links. So the title is a Martingale framework for trust, and I have two examples from ancient Egypt about that sort of system we're thinking about for trust. You could also think of a startup company. Okay, so suppose you in a startup company, or maybe someone building a pyramid is something like that, where you've got a big project, and you hire all these people, and then they hire more people, and it gets bigger and bigger, and you want to trust that it's a system that you're building is going to work. And if it's a startup company or a pyramid, you give somebody a job and you see how they do, and somebody else another job and you see how they do. And if they do well, then they have a reputation based on their performance. And the better they do, the more likely you are to use them, for more important positions. And if they don't do as well, then maybe you'll use somebody else instead. So constructing a giant pyramid is a big project like that. And just imagine organizing a trustworthy, dependable crew to do that. I gave this talk in Cairo, by the way. There's this giant obelisk in Aswan. I don't know if you've seen it before. It's a granite mountain, and they were 3,000 years ago trying to cut what would have been larger than any obelisk that we now have standing. And basically, if you start cutting into this rock, you have to kind of estimate where this obelisk is going to be. And you start cutting, and then you find that there's some cracks somewhere. So you're going to have to do maybe a somewhat smaller obelisk with a slightly different orientation, and so forth. And there you want to probe. You have kind of an estimate about whether there's a big obelisk in there or not. You don't know when you just see a mountain of granite. You start chipping away and trying to find the obelisk. And the question is there a big obelisk in there or not? Yes or no? And where should you start chipping next to try to decide that? Where do martingales fit into this? So, martingale is classically a good model for a gambling, amount of money that you have if you're gambling with playing a fair game. So you're going, say, between 0 and 1 unit of money, and you start out, and then the amount of money a gambler would have goes up or down. But if it's a bounded martingale, it has to converge, and typically it'll converge either 0 or 1 if it doesn't run out of movement. If it keep probing enough, if you can eventually identify either 0 or 1, you should get to the end. So you should eventually, you have an estimate. I think there's a 60% chance there's an obelisk with over 1,000 tons there. And then as you go on, your estimate of that probability would go up or down, and it's a martingale. And eventually, when you're done, you would know, yes, there is an obelisk there, or there's not. So here's some notation. So a trust framework is a pair, e.g., E is a finite set. We call the elements of E links, and each link has a state, either 0 or 1. Okay, and then the state of the network is just the vector of all the link states. And so 0, 1 to the E denotes a set of all the network states. And then G is a set of good network states, which is a subset of all the possible link states. So then a model within this framework is a way to specify a lot of examples, okay, or instances. So ST reachability model is the following. So the E then would be the set of edges on a graph. Okay, here's 4 edges. And then G is a set of network state, and there's also node S and T are distinguished nodes, a source node and a destination node. And then G is a set of network states with an all-one ST path. Okay, that means a path from S to T of links, all that have state 1. Okay, so G in this set would be 1, 1, 0, 0. That means 1 on links A and B, and 0 on C and D. Or it could be 0, 0, 1, 1. So C and D, those are state 1, or C and D could be state, A and B could be state 1, and D could be state 1, or they could all be state 1, whatever. Those are the good sets. Okay, so the problem would be in this to determine whether the state is good. In other words, is it in G or not? And based on some observations, and I'll describe later what the observation model is. Another example is graph connectivity, which is pretty related to that one. So E is a set of links in a graph, again, and G is a set of network states such that the graph is connected by all 1 links. So you look at the links that have, I should have said connected by the, I should have said by 1 links. So here, if green are the edges that have state 1, then this is a good state because it's connected. Any node can be reached from any other node by the links that have state 1. Okay, or equivalently, G is a set of network states such that an all-one spanning tree exists. Some tree of, there's n nodes, and you'd have n minus 1 links, so that with no cycles. And that should all have state 1. Okay, so here the problem would be to determine whether the graph is connected or not. If there's any question at any time, let me know. A couple other ones we're thinking about, the majority vote model. So E is a finite set. They might be Supreme Court justices in the US, or 9 justices. And G is a set of network states with a majority of 1s. Okay, so you want to know, is there a majority of 1s? And the final model here is a parity model. E is a finite set. And then G is a set of network states with an odd number of 1s. So I want to tell that the number of 1s is odd. So those are the 4 models for a good set. But it's basically any subset of 0, 1. So all of combinatorial optimization can fit into this. Here's some notation in case G is upward closed. And upward closed means if a state is a good network state, then if some of the zeros are turned into 1s, it would still be a good state. Okay? And all the examples except the parity model I talked about satisfy that. If there's a path from S to T with all 1s, if you turn some more edges, links, from 0 to 1, then you'd still have a path. Or if it was a connected graph and you turn some more zeros to 1s, it'll still be connected. Or if you have a majority of 1s, if you have more 1s, it'll still be a majority. But if parity is odd, if you change 1 link from a 0 to a 1, then it won't be odd anymore. So that one's not connected. So if it's upward connected, then we let A be the set of minimal states in G, and B be the set of maximal states in the complement of G. So for ST reachability, the minimal states in G would be 1, 1, 0, 0. That means have path A and B have 1s, and the other 2 are 0, or 0, 0 and AB and 1, 1. So these basically correspond to paths from S to T. And if you can find a path that's all 1s, then you know there's a path from that S is connected to T. It's kind of like a proof that you have a good network, if you can actually find the path. And B, these are elements that are in G complement, so these are maximal. They have as many 1s as possible such that the network is not good. Network state's not good. So B consists of sets here that have a 1 in the top for either A or B or 1, and C and D, and either C or D are 1. Okay, and if you have if you know that you've got zeros, like if you knew that A and D were bad links, that would be like a cut. If you knew that those were 0, then you know that there isn't a cut, and you don't have to look at the other edges. Okay, so these are kind of, so A and B would give you, we use A to get a proof that we have a good set, and B to have a proof that you have a bad set. Okay. And another example is for the majority vote model. A would be the set of network states with exactly a majority of 1s, just exactly enough 1s to have a majority. And B would be the set of network states such that you're short by 1 vote. You exactly miss the majority by 1. Okay. And if you, again, you could prove, if you could find a particular majority, say these 5 people out of 9 are going to vote yes, it doesn't matter what the other 4 are going to do. Or if you could find 5 people that are 0, then it doesn't matter what the other 4 are going to do. Okay, now I'm going to get to the statistical model. Okay, and by the way, when thinking about this, since there aren't any theorems yet, if you have a good idea for one, you can start changing the model a little bit. It's not like set in stone. But here's the model we use for observations. So we have a random network state X, and we assume that these X of E's are either 1 with probability pi E or 0. So, and we also assume they're independent. So independent Bernoulli random variables. And then let chi be the indicator function that the network state is good. Then we can calculate the probability of the network being good. It's just the sum over all the good states of the probability of getting that good state. Okay, just the product over the links E that are supposed to be in state 1, pi E, and then the links that are supposed to be in state 0. So this would be 1 minus pi E. The bar is 1 minus. And then this would be xe bar is 1 for the links that are, if x of E is 0, then, yeah, so this term is either pi E or 1 minus pi E for each link E, depending on whether the link is a 0 or 1 for state X. Okay, so it's just, so this is the probability that state X is the true state, and then you just sum over all those that are good states. Okay, and we assume that X is fixed for all time. So if you're going to do a simulation, before you start simulating anything, that state is drawn and it's fixed. And then, therefore, chi is also fixed before any observations are taken. Okay. So then, a decision maker would like to accurately determine chi, whether the network is good. So, and it can probe one link at each integer time, t bigger than or equal to 1. And then in response to each probe, the decision maker observes y of t, which is generated by a binary symmetric channel with some known crossover probability a sub e, where e here is the link that's probed. And most simulations and things we've done, a sub e is the same for all links e. So then we just call it a. So if you probe a particular link, the state is either 0 or 1. And then think of a sub e being 0.6 or some number bigger than a half. So if the true link state is 0, then the observation is 0. And if the true link state is 0 with probably a sub e, or it's incorrect with probably 1 minus a sub e. And if the true link state is 1, then the probe value gives 0 with probability 1 minus a sub e, or the correct result with probability a sub e. So you've got this graph here, trying to figure out if it's connected, and then you can sort of put your finger or probe on each link, and you get this estimate. Yes, this link is good, or no, the link is not good. And then what we're focusing on is finding a probing strategy. So a probing strategy determines which link to probe at time t plus 1 based on the observations up to time t. Where should you probe to try to find as quickly as possible, in some sense to be determined, maybe by you, to determine as quickly as possible, is this a good network? Okay, of course, if these a sub e's are not equal to 1, you'll never be able to determine 100% with 100% reliability whether it's good or not. But it's like this martingale. It should be converging to 0 or 1, and you want to get the convergence to be as fast as possible. So there's Bayesian updates here. So we let P sub ET be the probability that the state of link E is 1 given all the observations up to time t. That's what ft means here. Okay? And then by Bayes' rule, since the links are independent, if we've probe link E n sub ET times, and in k sub ET times we observe 1, and the rest of the times we observe 0, then we're just estimating whether, is this binary random variable a 0 or a 1, where a sub e is the crossover probability in the observations, and pi sub e is the prior probability that the link is in a good state. And it's just Bayes' formula, just a function of these variables, phi, where it's just usual Bayes formula, right, like that. Okay. Or you can compute it recursively. The simplest case may be of nonlinear filtering. So the estimate at time t plus 1 is the same as the estimate at time t if you didn't probe link E. If you do probe link E, then if you get a 1, then this is the new probability, and if it was a 0, that's the new probability. So those get updated. Okay. And then we let g of t be the probability that the network state is good, which is the expected value of the chi given f of t. And then we can write that as using those conditional probabilities. And that's exactly the same formula I used before, except the pi sub e, the prior probabilities, are not replaced by the posterior probabilities after t observations. And so in particular, g of 0, that means after 0 observations, we start out with our expected value. And then these random processes, the p of et and g of t are martingales, because they're all expected values of fixed random variables given increasing information. And here, if a sub e is not equal to a half, so that you don't just get random coin flips out when you observe something, then if you probe link E infinitely often, then the conditional probability that the link is good will converge to the actual state, either 0 or 1, depending on what the link is. It'll eventually get there almost surely, and therefore probing strategies exist so that g of t also converges to the true value, 0 or 1. Okay? And they're martingales, and again, we want to see how fast they converge. Okay, and how do you measure rate of convergence? You can measure it the way you want. We do some simulations that you might think about when you're formulating this. So since g is either converging to 0 or 1, and which one it converges to depends on the true state, we looked at something that converged to 0, whether g converges to 0 or 1. So we take h here to be a binary entropy function. It's a concave function that goes between 0 and 1. And it happens to be symmetric, but symmetry is not that important. But it should be a concave function that's 0 at the endpoints and strictly positive in between. It also could be g of t times 1 minus g of t, for example. And we call that the uncertainty. And maybe there's some theorems that are good for one choice of h, but not for some other choice of h. So we're not really, there's nothing really special about the binary entropy function. By the concavity of h, u is a super martingale. It means it's got negative drift at each step. Also, if h is the binary entropy function, then u of t would be the conditional entropy of chi given the observations. Because the entropy of a binary random variable, if its probability 1 is equal to p, then the entropy is h of p, and then we're just putting in this g, which is like the probability that network state is good given the observations. Okay, so So then U would be the conditional entropy of G, and the initial value of U would be the entropy of the network state. And then if you look at this, this is we expect the entropy to go down. So the expected value U t plus 1 minus U of t should be negative. That's the drift of the uncertainty is negative. I'll put a minus sign, that makes it positive. So this will be positive. And in case H is the binary entropy, this is the mutual information between the network state and the observation y of t plus 1, given the past observations. So, that's your expected reduction in uncertainty is the mutual information. So our focus is to find probing strategies so that U converges to 0 as quickly as possible, in some sense to be determined. So do you have any suggestions for probing strategies? This should be very suggestive of one.
Maximize that.
Maximize that. Yeah, that would be a greedy strategy. We call that the greedy strategy. Just wherever you are, try to maximize the mutual information that you're going to get out or for the next step. Or for any H, it's the reduction of uncertainty. Once you define the uncertainty that way, choose a link to maximize the reduction of uncertainty. Okay. First is a uniform probing strategy. Repeatedly cycle through the links in a fixed order, probing each link once in each cycle. I just go through there. That's sort of a benchmark strategy we looked at. And then the next one is the greedy probing strategy. So given f of t, the information that you have, for each E, compute the expected reduction in the uncertainty about the network were you to probe link E. And do that for each link E. And then see which one will give you the greatest reduction. And so that would be, it's like an index. In fact, there might be some multi-armed bandits in here somewhere. There's also some percolation theory in here, by the way. So, but you want to probe that to maximize that. All right. It turns out that's difficult to compute. To calculate this U of t, you've got to calculate, if this is a large graph, what's the probability that this graph is connected given the probabilities on the edges? That's something we use in our undergraduate probability class all the time, except we only do it with 5 edges. You know, we condition on the one in the middle. Maybe you've all, a lot of you have taught that already. I don't really have a good idea how to do it with 1,000 edges. And then for each of these 1,000 edges, suppose you were to increase your estimate of which, a given increase or decrease, your estimate of a particular edge, how will that change your estimate of how the whole network is? Okay, so that's why this is difficult to compute. So we looked at the k-empirical greedy probing strategy where you try to estimate that based on past performance. So we follow uniform probing for k rounds. Then we switch to a greedy strategy using estimated values of this decrease by seeing what the actual decrease was. Okay, it's the average of the decrease. This still requires computing this U, by the way, which just computing the U, the uncertainty is difficult because you have to calculate the probability the network state is good. Okay. Okay, the best chance probing strategy, and a prelude to this is when I talked about upward closed good sets. Okay, because if you can find a particular path that's good, then you know that the network state is good. So you want to focus here on finding a particular path that's good. So you find an X star in A that maximizes this probability X is bigger than or equal to X over all X and A. So this would be find, in the case of ST connectivity, find the path that's got the greatest probability of being a good path. And then probe a link on that path with the smallest PET. It's like the weakest link. Okay, you probe the weakest link on the best path. And what we're doing is trying to seek a certificate for the network to be in a good state. So you think the network's in a good state because there's a path here. That's your best chance. See if it works. And you start probing the worst link. If that link gets stronger, it's a martingale. Whether the probability it's good or not, it's a martingale. If it gets stronger, then that whole path has a better chance, and you'll keep probing that link. If that link turns out to be a dud, starts going down, then some other path will emerge as the most likely path, and then you'll start, testing the weakest link on that one. Okay. So for the three models that are upward closed, this best chance strategy becomes the best path strategy. So you probe the worst link of the best path from the source to the destination. Or it becomes the best tree strategy for connectivity. You want to see if the graph is connected. So you find a spanning tree with the best possibility of having all the links being 1. There's algorithms for finding a maximum weight spanning tree. In fact, that's a greedy algorithm. So you could use that. Or for the majority model, this best chance strategy becomes the middle link strategy. Because if you think you have a majority, so you think there's 5 justices that are going to vote yes, look at which one's got the smallest chance of voting yes, and probe that one. It's the one on the edge, and try to strengthen that, the edge. And if that one goes down, maybe below someone else, maybe you should be probing someone else. If it goes up, then maybe that won't be the weakest one anymore, so try probing another one. Okay, that's what that strategy suggests. Okay. Let's see. So here's the best tree strategy illustrated. And this is an example without an all-one tree existing. And I see up here, this is supposed to be all blue links here. And then as you probe them, they either turn green, it's hard to see, these are green links, or they turn red, because they go up or down. And so here, for some reason, these links were probed and they were red. It got red, so they stopped getting probed. And then a link here was probed, it was green. And the best tree strategy was run here. So it keeps looking for a tree with the greatest chance of being all ones. In the end, it found that, you can kind of see all 5 links here got probed quite a bit using the best tree strategy. So you're trying to find a tree, but it pretty much visually it sort of found a blocker to a tree, because the graph can't be connected if all 5 of these links are bad. And this kind of suggests the next strategy we chose, or the final one I'll talk about. This is a similar thing when their tree does exist. Call it the best chance, worst block probing strategy. Okay, because you don't know ahead of time whether the network is good or bad. Okay, so maybe you start looking for a path, and every time you go to a path, the worst link is really bad, and so you keep cycling through these. Maybe you should, at some point, say, maybe you should prove the network is bad rather than trying to prove the network is good. So the best chance, worst block strategy is to simultaneously track both of these, and whichever one looks like it's winning out. If it looks like there's a better chance for the network to be good, then probe the weakest link on the best path, or the weakest link in the best minimal, the best set of A. Or if it turns out the bad state is winning out, then probe the best link and the worst cut, the worst block, and alternate between those two. Okay. So that's what we did. So X star maximizes over all A. These are the minimal sets of the probability of the ones being one, of the X and either are 1, probably that those are actually 1, that they're all 1. Okay, so this would be, if you're looking for a path from S to T, find the path that's got the largest probability of being good. So this is only probabilities in that are x of e are 1. It doesn't matter what the link states are for the other links, because they're not on that path. Same thing in y star, but this is the actually that should be the maximum of y and b. You look for links that are state 0 here, and so this is a probability that you have a bunch of zeros that are enough to block. So actually, also these products are just these two probabilities. So see which case is stronger. So if the chances of x being bigger than x star is bigger, so you've got a sort of better lead on proving it's a good network, then probe a link with the minimum value of PET among those. Otherwise, probe a link with the maximum value of PET among those that YE is 0. And this gives the best path, worst cut strategy for the ST reachability model. So actually, this model is the one case where we can get an upper bound and a lower bound on the uncertainty for very large graphs, because the ST path is the shortest path problem, where we use for the product of the probabilities or the sum of the log of the probabilities. And the blocking set is also, you know from percolation theory, the blocking set is also, and you can formulate that as a minimum path problem. So you got these two kind of dual problems going, and so you can get upper and lower bounds and see how things converge even for large networks. Okay, and for the parity model, we're sure this is optimal, but we don't have a proof. But it depends on what you mean by optimal, too. We call it the closest to 0.5 strategy. This is intended for the parity model. So probe a link E such that PET is closest to a half. Okay. The previous one, everything I suggested at this point is really intended for the upward directed model, upward closed models. This one's just for the parity model. So you just want to determine whether you have an even number of ones or odd number of ones. And it's kind of invariant. You can flip the zeros and ones. So all that matters for the PETs are how close they are to 0.5. Okay. I mean, if you knew a link was 1 with probably 0.7, you could just flip it, and then it would be a 1 with probably 0.3. It's just the same. Okay. So you might as well probe the link such that the PET is the closest to a half. And that should definitely be optimal in some sense. So I'm going to talk.
Should read
what?
Exists the notion of optimality, which makes this.
Yeah, there should okay. Under what definition of optimality is this optimal? Yeah. Okay. So I wanted to discuss now defining optimality. What do we mean? The first thing, if I really wanted to get really serious and do dynamic programming stuff, I would use dynamic programming and something. And we know these things are going to converge to 0 or 1, so how fast? So we could use the rate of convergence. So maybe you just want to compute the rate of convergence. So does that exist? And so let's just look at a network with one link for guidance here about how to formulate the problem further. So we have just one link. So there's two states of the link, which are the same as the states of the network, and we just want to tell if the network is in good state. So we drop the subscript e on these variables because there's just one link. And then, so n of t would be t, because the number of times we probe link 1, and there's only one link, is t times. And then g of t will just be given by this phi function here. And the uncertainty would be given by h of phi. And we could look at the expected value of the uncertainty. We can calculate that. The median value of g is close to the mean, right? In fact, the difference between the median and the mean of a binomial random variable is less than the maximum of p and 1 minus p. Nice result from literature. So the mean of g is very close to the median, But then u is this nonlinear function, but for large values, you're sort of on one half getting close to 0 or getting close to 1. And so the median of u gets close to h of the median of g. You know, if h was a monotone function, that would be true. And then the median of g is approximated by that. So that's sort of an estimate for the median. And I just want to sort of distinguish between the mean uncertainty and the median uncertainty. Because here's a simulation for one link. So this is the number of observations here. And this is for crossover probability 0.6. And the prior probability is 1/2. And h of p is p times 1 minus p for this. So the mean uncertainty and the simulated mean are given by this upper curve here. And then the median, or approximate median, is given by the blue curve here. The approximate median is a lot smaller than the mean uncertainty. Why would that be? Well, you're taking expected values of something between 0 and 1. And median means that half of the sample paths should be less than this number. Okay, there's not, and then half of them are bigger than that number. And just the ones that are bigger are a lot bigger, and the ones that are smaller can't be much smaller because it gets so close to 0 there. So here's actually 20 sample paths. And so now you maybe can believe that this is actually the median, or down here, that half the paths at any time are above it, and half of them are below it, whereas the mean is a lot larger. Okay, so if you want to do criteria for optimality, maybe you should look at the mean or the median. Maybe the median is more reasonable to use than the mean. Okay. Here's just we try extending the median approximation to larger networks. So could you find the median for a larger network? So here's a graph in 2 different network states. This is 0, 0, 1, 1. So here there's a good path, CD. And here it's 0, 0, 0, 1. There's no good path. This is the only link that's good. And here's a simulation where we're using the greedy strategy. We're trying to reduce the mean uncertainty as much as possible at each step. And this settles down to purple and a triangle. Links C and D, those are the good links. So the greedy strategy settles down and just keeps probing those 2. Okay, this is a number of probes versus time, and the greedy strategy just stops probing these other 2 links because it's zeroed in. It might be wrong, but I mean, well, it's not wrong in this case because we know the graph, but it doesn't know it. So it's zeroed in on what it thinks is the right state. It just keeps probing those, and those will keep going up, and those other 2 won't be probed. Similarly, for the other one, it's zeroed in on a cut. It keeps probing 2 links that are both state 0 that are enough to cut the network, and then it stopped probing these. Okay. So if you want to look at the median, what it looks like at least for the greedy algorithm, we're not sure what the optimal algorithm does. Maybe the greedy algorithm is optimal in some sense. We said no, it's not optimal because we looked at the mean, and there's a lot of counterexamples, but maybe we don't. Maybe there's some criteria for which some of these algorithms are optimal. Okay, so this went up here, but this suggests that the median of the uncertainty should be pretty much like the one-link case, except you divide the time by C, where C is the number of links that are probed infinitely often. You know, that we think that some links will be probed infinitely often, and then other links won't matter. There's no reason to probe all of the links. Yeah.
Just going back to those 2 examples, in the first one, you could presumably expect it to do that.
Yeah.
And in the second one, it might have chosen the other cut, might it? I mean,
yeah, for that particular graph, there's actually
there's 2 cuts.
2 cuts. Yeah. So
One of them gets ahead first of all, and then it sticks with it.
That's what it did in this particular simulation. I'm not sure. It might bounce between two. I think part of the reason it's hard to calculate is it's kind of a broad bottom. I think there's right, but it could have done A and C a lot, or B and C, because those are two cuts. And so, is it better to probe at just A to show that there's no path, or just B? And what you're really interested in is the product of the probability that they're both 1. Okay, the product of the probability they're both 1 should go, if they're both going down exponentially at the same rate, the product is the probability of two exponentials, and that would also have the same rate. So it'd be like e to the minus I1 of t times e to the minus I2 of t, where I1 and I2, wait, e to the minus I1 times t, e to the minus, actually, it'll just be I, e to the minus I times t1, e to the minus I times t2, where t1 and t2 are the number of times you probe those two lengths. And it only depends on the sum, really. So, yeah, you might, so to the exponential order, it wouldn't really matter whether you should probe C half the time, but it doesn't matter that much, at least to the exponent, of whether you spend all of your time probing A or all of your time probing B. And the greedy algorithm happens to choose one and stick with it, but it would be almost as good to probe C half the time, A a quarter of the time, and B a quarter of the time. That would be the same. And it would go to 0, same rate, same exponential. The median would go to 0 at the same rate. And also, you could have multiple good paths. Well, if you weren't, it's a similar thing finding a good path. If you didn't care to know exactly which path is good, and you just want to know, is the network good? It might be a similar thing. All right. Okay, so that's an approximation. So then there's a bunch of slides that follow. I have this master's student, Charles Spuckler, who did a lot of simulations. And there are a bunch of them in here, and I don't plan to go through all of them. I'm just going to sort of flip through them, and I just come to the conclusions here. So the slides that follow present various simulation results. We used pi e to be a half, AE is 0.6. Each simulation covered 300 time slots. And we applied empirical averages of u, using u as g times 1 minus g for 1,000 samples for these two networks, 4 and 5 link networks. And this is small enough we could calculate u of t exactly for all of the graphs. And okay, so this is like a typical graph here. So the uniform strategy did pretty badly. And then for the best strategy, the ones that were the best, the greedy did quite well most of the time. And this worst cut, let's see, the best path, worst cut, that's this one down here. Sometimes that did a little better than the greedy strategy. So we stopped trying to prove the greedy strategy was optimal even for this. Maybe it is optimal for some criteria, but if it's the expected value of the uncertainty using the function h is p times 1 minus p, it's not optimal. But these might be close to, I mean, I'm sure they're close to optimal for this small of a network. Okay, here's 20 iterations of ST connectivity using greedy. Okay, so similar graph to what we had for one link, and here's the approximate median. So the median approximation works pretty well empirically. All right, so I think I skipped. Okay, directions to explore. Okay, so this is like where we think is important or interesting, anyway, to look at. So what types of results would we want to look for? One is a small network where you have exact optimality. And we were pretty convinced that for the majority vote, if you got 9 people and you want to see there's a majority one, you should be probing the one in the middle. But we don't think that's true anymore. There's some example, depending on the grouping, that we don't think that's a best way for several different optimality criteria. The only one we really believe, that I still believe really deeply, it's got to be true, is that for the parity model, the one closest to 0.5 has to be optimal. You have to have a nice criteria to make that optimal. So that's for small networks. Then the asymptotic behavior for large times, for large networks, or for any network, that would be sort of like this median. And it basically comes down to saying, in the end, you don't have to probe all of the links infinitely often, but just the ones that are that look like they're winning out. Also, this model, the link states are either 0 or 1. You could have another model where the probability of a link being, that a link isn't always good. It just has some probability associated with it. And then you might want to identify what's the probability that this network, or the probability that if you send a packet on this end that it would make it to that end. Maybe you want to estimate that, in which case you probably have to probe every link infinitely often, but some lesser than others. Okay. And then the asymptotic behavior for large networks where you let the network size go to infinity and not so much the time going to infinity. Improved probing strategies. And this is where we think percolation theory or some kind of computations can come in. So we looked at the greedy algorithm and all the algorithms for this ST connectivity quite a bit. And we can be pretty confident that there's a path existing in the middle section of this network just because there's so many paths. And some of them have to be good. So really the question is getting away from S and getting to T. So you want to probe more on these ends. And the greedy algorithm, if it's really large, it doesn't really know where to look. Okay, so you could do some simple. We've tried various heuristics. I mean, look at all the paths from S to T, count how many of them go through each edge, and probe the edge that's got the most paths going through it on the grounds that it's pretty central, and we should know about that one. So there may be, we're sure that for large networks there's improvements over these strategies I talked about. Okay. Then for more complex, you can have more complex models. So that this x of e, instead of being either 0 or 1, it might be a number between 0 or 1. We require a distributed probing process, so you can only, going back to where we started, the central prober might not be able to reliably probe someone. So you ask someone else, how good do you think that link is? And then you sort of build out this trust framework where you sort of from the edges. So that remains to be explored. And thank you. That's what I want to talk about today. Any questions, comments, or formulations of optimality? Yes?
I would like to ask you, if you have a graph and you know a lot about it, such as it's a social network, and
like a random graph?
Yeah, but I mean, like, you have extra information, you know that effects of homophily exist. So if you probe one link, then you have more confidence of what is going around.
Oh, so maybe not independent link states?
Yes.
Yeah.
Then could you develop a kind of more context-aware strategy?
We could put that into this more complex models. I don't know. That's a good question. Yeah. Someone was doing Facebook, as Paul Cuff at Princeton told me about this. They show you there's 100 cats, and they want to rank ordering of the cutest cat. So anytime you log into the website, you just get these 2 cats, and you say which one's cuter. Okay. And so it's a binary observation, and if you show these same two cats to two different people, they don't necessarily agree with each other. So it fits the model very well. And the problem they want to come up with is how to choose which two cats to show to people. Okay, so at first you could just choose two at random, so show all pairs sort of with equal probability. But then at some point you want to start showing cats that are kind of close to each other, trying sorting out the order more. And it depends on, do you want to get the top 10 cats, or do you want to get the first cat? I mean, what's the most important thing about the orders? But there's a similar idea to try to look at uncertainty and some heuristics. There could be a lot of problems like this, and we just want to come up with a really simple model that maybe we can say something about. Yeah.
How does this relate to like various type of learning strategies, like reinforcement learning, for example? Yeah, I mean, do these people in those communities bother about optimality? Or?
I don't know. I'm sure there is related theories here, but I don't know how reinforcement learning, what it would say to do here. I was hoping maybe to run into a reinforcement learning expert. I mean, I think this is a problem that it's like a lot of problems, kind of, and so just sort of gathering approaches. And, yeah, that's a good thing to look into. Okay, thank you.